The Tuesday afternoon session, the first speaker is going to be Ryan O'Donnell, who will talk about testing surface area.
Thanks, Rocco. Thanks for inviting me to this. Okay, here's what you need to know. Oh, this marker is not very good. This is a joint work with Kothari, Nairi, me, and Changgang Wu. And actually, I don't normally give acknowledgements, but I'd like to actually acknowledge Adam Clivens, who has contributed a lot to the early stages of this work. Okay, so the title, you can kind of guess what the subject will be, but I can tell you the motivation. It actually came from a paper that I wrote with Clivens and Rocco Servideo in 2008, and it was a learning paper. And the learning result in that paper was the following. Let's C be the class of all sets F in Rn with surface area at most S. Oops. And actually in this learning result, we were thinking of Rn as having the Gaussian distribution, because it's quite natural in high dimensions, especially for learning. So in fact, I actually mean the Gaussian surface area here, which was mentioned in Elkanon's talk. I won't define it, but basically you integrate the Gaussian PDF over the surface. And the result in that paper is we gave a learning algorithm for this class. And in fact, it was an agnostic learning algorithm. Say in 2 seconds what that means. Learnable under the Gaussian distribution, as I said, in time, n to the order of s squared. Okay, and that's pretty nice. There are actually quite a few sets that have surface area, Gaussian surface area at most an absolute constant, like the set of all ellipsoids of any size has surface area at most 1, so that would give a polynomial time algorithm. Any polytope with polynomial in n many faces has square root log n surface area, so it gives an n to the log n time algorithm for this class. And this agnostically means that actually the set doesn't actually have to have surface area at most S. You can talk about non-convex things. Actually, the set of all convex sets is also interesting. They have surface area at most n to the 1/4. So that gives you a running time that's like n to the root n, sub-exponential even for them. But you can also get results for non-convex sets.
What do you mean learnable?
Basically the model is that you get examples. So you get randomly drawn Gaussian points from the Gaussian distribution, and also whether or not they're in the set. And after about this many draws and time, you have to output a hypothesis set which is close to the true underlying set F in Gaussian measure. And actually this agnostically aspect means that it works even in a very challenging error model where you don't have to assume that the unknown set has surface area at most S, even if it's only 90% close to such a surface, such a set. Like if you take a set of surface area S and change it on 10% of Gaussian space, this algorithm will still find a good hypothesis that agrees with the set on 89% of Gaussian space. Okay, so that was the learning result. Now the running time is, can be a little bit slow. So this is actually, I think, a good example where this motivation for property testing of testing before learning makes a lot of sense. It might be reasonable if you're given, let's say, black box access to this set F. You can query a point and see if it's in the set or not. To first try to check really quickly if it has surface area at most S, or is close to having surface area at most S. And then if it does, then you might want to actually run this, medium fast algorithm. Okay, so this is our motivation to try and answer this question. So more precisely, what it would mean to do test surface area in the property testing framework. You want something that looks like this. So sort of the input, you have black box access to a set F. And this was about the Gaussian setting, and we're going to actually eventually talk about the Gaussian setting here too, but let me stick with the more familiar setting of the normal surface area and normal sets. So let me, just for scaling, say that it lies somewhere inside the unit cube, just so you know where to look to start. Pardon me? There's an unknown set F that you're sort of promised lies inside the unit cube, and you can query any point in the cube and find out whether or not it's in F. And you're also given a target surface area S and some error parameter epsilon. And what does the algorithm do? It can like query q randomly chosen points, not necessarily uniformly random from the q, but according to some clever distribution, and learn if they're in F or not. And after it does that and does some computation, it has to either output yes or no, which basically means whether or not it thinks the set F has surface area at most S. Okay. And the goal in property testing is to mainly focused on the query complexity. You want to minimize Q, although our algorithms will also be fast. Yeah. We'll have results for both, but let me just focus on the standard Lebesgue surface area. Okay, so no, here the algorithm has the property that it actually doesn't use queries. It just uses purely uniform independent random examples, and it uses about this many queries too, or it uses about that many examples and time. Okay, and it just doesn't output yes or no for some reasons. It has two things that it's trying to satisfy. The first one is called completeness. And this means that if the unknown set actually does have surface area at most S, the target, then you should output yes with high probability. Let's say at least, I don't know, 99%. You can boost that to something higher if you want. And as usual in property testing, the soundness condition is slightly more subtle. You can't just say that if it has surface area bigger than S, then you output no with high probability. And I'll draw a picture explaining why shortly. But if you're familiar with property testing, you'll recognize this kind of thing. We want that if F not just has small surface area, but F is epsilon far from all sets G with surface area at most S, then the algorithm should output no with high probability. Okay. And what does epsilon far mean? Here we just mean that the volume of the difference is at most epsilon. Okay. And actually, in property testing, it's usually nicer to think about the contrapositive of this condition. So let me write that. Equivalently, you want it to be the case that if F is such that the algorithm outputs yes with probability even at least 1%, it should mean that there exists a G which is epsilon close to F such that the surface area of G is at most S. Okay, these are equivalent. Yeah? Is there some assumption of the volume effect? No. No. In fact, the important thing for us, as I'll say now, is actually there's no assumptions made on F at all. Okay, so for example, this is basically like you're given black box access to a set, and roughly speaking, you want to estimate its surface area, which is quite similar to, you know this a long body of work in Markov chains literature about estimating the volume of an unknown convex set that you're given black box access to. It's not hard to show that if you can do that, you can use similar techniques to estimate its surface area. This was done by Belkin, Harianen, and Nyogi. But this is quite different model because we don't assume convexity at all. We don't assume anything at all about F. Yeah.
So if you have surface area, will your other algorithm be able to find to learn some body with small surface area close to F?
Yeah, so that's a good point that I was going to say. I mean, this actually fits quite nicely with the fact that the learning algorithm has this agnostic property, which means that you don't really have to have the set, have surface area at most S, as long as it's epsilon close to having surface area at most S. The algorithm will run in time as though it had surface area S.
defined by a convex set, right?
I don't understand. I mean, you're.
Positive and negative points. These are inside, those are outside.
Mm-hmm.
And I ask him, find me the smallest surface area.
It need not be convex. The information can
The
exclude
information
it.
can
Yeah.
There's more information than the points that you find.
Yeah, so I mean, a picture to keep in mind. So actually, this problem is almost equally interesting in 2 dimensions as it is in n dimensions, unlike the case of the classical, estimating volume problem. So a good picture to keep in mind is like, here's the cube in 2 dimensions, and you could have a set that's like, maybe it starts to look like it's a nice convex set, but actually it has some like a weird tentacle here, which has, by making this really thin, you can have like negligible volume, which means that like a black box query algorithm will like never notice it, but it has like, constant surface area. This can be quite, actually arbitrarily large surface area. Okay, so because of the possibility of like these tentacles, for example, you kind of have to work in the property testing model if you want to work with absolutely no assumptions about the convexity of the set. Okay. There's a slightly more subtle other problem. Like you could have a set that looks like this and has like some super wiggly boundary at a small scale. You can make the surface area or perimeter in 2 dimensions arbitrarily large by making this very wiggly, but like, if that's the negligible area difference from just a flat size. So a black box algorithm can't really notice it.
So I guess it's implied that the volume is at least epsilon, otherwise you're epsilon.
Right. If the volume is not, so for example, testing volume in this setup is easy because you just have to query about 1 over epsilon points randomly and see if you notice something. And as Motor says, actually, if the set F happens to have volume less than epsilon, then by isoparametric inequality, its surface area will also basically be less than. No, sorry, the other way around, actually.
Epsilon close to the empty set.
Right. It's epsilon close to the empty set, which has surface area 0. Okay. Good. I should also add, we have results when F is just a subset of Rn, and surface area is Gaussian surface area. But I'll just stick with the Euclidean case. Okay, any questions about the model? The problem? Okay, good, because I'm going to add one twist, which will allow us to state our results and also the previous results. I'm going to make the job of the tester a little bit easier, because in some sense we couldn't prove everything we wanted. So I'm going to insert a factor here, kappa times S. I'll call kappa the approximation factor. Okay, which ideally would be 1. But it's not such a big deal for us. It'll be something like 1.3, so it's not a crazy big factor. But it just shows, you only have to distinguish things that have surface area at most S from ones that are far from having surface area maybe a little bit bigger than S. Okay, so that'll make our job a little bit easier. Okay, still okay with the setup?
But it's not clear that kappa.
It's not clear that kappa is necessary. In fact, I'll show you, some results have no kappa, just kappa equals 1. No, yeah. That wouldn't make my life any easier. Okay, so let me tell you about prior work. So this problem was first appears in a work of Kearns and Ron from '98, just in the case n equals 1. Okay, which is still non-trivial. So n equals 1 means you have a set that's somewhere contained inside the interval. Maybe it's this. And its surface area is just, the number of endpoints, or twice the number of intervals. So this is the problem of you're given black box access to a subset of the line. You want to test whether or not it's a union of at most S over 2 intervals. Okay, so they worked on exactly this problem. They, on one hand, achieved very good query complexity 1 over epsilon, but actually their approximation factor was 1 over epsilon, which is very large. Okay, so they could only tell the difference between like S intervals and S over epsilon intervals. This was essentially improved in a recent work by Volkan, Bleh, Blum, and Yang. They also only focused on n equals 1, but they had no approximation factor. I mean, they just solved the problem precisely, kappa equals 1, and their query complexity was polynomial. It was 1 over epsilon to the 4th, so that's great. I mean, they solved it for 1 dimension. No, we'll see the algorithm in a second. It's, well, you'll see the algorithm in a second. Okay, and now I'll tell you our results. So we looked at higher dimensions, which actually, as I said, it already becomes quite interesting in the case n equals 2. And really all the main ideas are in that case. Although we also got something for n equals 1, I suppose. We got, kappa equals 1 with very slightly better query complexity. This is not a big deal. But we actually got, for any kappa that's strictly bigger than 1, we got linear complexity. Okay, so this hides a constant that depends on how much bigger than 1 you are. It's like polynomial. So that's good. If you allow yourself a little bit of slack, then you can get even a linear query complexity. But we also got results for higher dimensions. So for n equals 2, actually all our results are basically linear query complexity. This is for any kappa, which is strictly bigger than, kappa 2, which is 32 over 3 pi squared. That's 1.08. For n equals 3, we got the same linear query complexity for any kappa bigger than kappa 3, which is 9/8, which is 1.125. And in general, for general n, we got this query complexity for any kappa greater than kappa n, which is, does anybody see the pattern? 1, 32 over 3 pi squared, 9/8. What's the general case? No? I'll give it. It starts with a 2, yeah. 2, n plus 1 squared, n over 2, choose negative a half squared. Oh, there's no square here. Yeah. No, I mean, this is like the most compact and jokey way we found to write it. It's really like the ratio of some gamma functions. But you can theoretically express it this way. Yeah, so it goes, as n goes to infinity, to 4 over pi. Which actually was very cool to us. We didn't expect this. And what it means is, this is, 1 point something, 1.27 maybe. It means kind of this, in some sense, evades the curse of dimensionality. I mean, for all n, you just get this one result. If you allow kappa to be 1.27, linear query complexity. So this was kind of surprising to us. Yep. No, it's really just if you want to get kappa n plus eta, then the query complexity is 1 over epsilon eta 2.5. Okay, so that was neat. We were certainly at first willing to tolerate something that involved n, but it turns out you don't need to. Okay. Oh, and also, oddly enough, in the Gaussian case, the result is just 4 over pi for every dimension, and the same linear query complexity. Okay, so let me...
Gaussian case?
Yeah. I think so. Actually, we didn't quite think this through. I mean, there is the issue of that it's only like epsilon far from being, but I mean, I think you can just try this for different values of s, and I think that will do something. I didn't think about it, though. Okay. Yeah.
You do have to worry if your set has an epsilon set on which you can change the surface area.
Well, it will be some kind of core surface area.
Yeah. I didn't think it through. It's worth thinking through. I should add that, as Scotty indicated, there's actually no reason to believe that you need such an approximation factor. And one reason I want to talk about this result is I think it's a very great question to just get it, kappa equals 1. There's no real reason why this kappa is necessary. And in fact, our algorithm may already work. We just don't analyze it correctly. Okay, so about this algorithm, after a little thought, Well, does anybody have a suggestion on how you would try to estimate the surface area of an unknown set using, yes? Very good, thank you, Alkanon. I might even phrase it a different way. Well, I'll get to the noise sensitivity, but as Buffin's needle. Okay, so, I mean, so just remember the setup. Let's say we have F. It's a subset of, well, I would write 0, 1 to the n, but actually, for technical reasons, it's a little bit nicer to let it be in the torus rather than the solid cube. Then you don't have to worry about, like, whether if a set's on the boundary, does that count to the surface area or not. So just imagine that these things wrap around. Anyway, it's not a big deal. And let me also write F for the plus or minus 1 indicator of this set. So, you know, Buffin's needle, you drop the needle, it helps you estimate the surface area, right? So, basically, at a high level, the way Buffin's needle work is you pick a random needle. It just means a line segment. Let's say x, y of length delta. Think of it as small. Okay, so that just means you pick like a random point in a random direction, and you go y from x to y. Maybe that's one, that one, etc. And then one thing you can do is try to see if it crosses the boundary. At least in the property testing model, it's natural to just query f of x and f of y. That's two queries. I mean, that's checking if x and y are in, and check if they're not equal. Because after all, what is the surface area really? But you like sort of look at all the points that are within distance delta of the boundary, take the volume of that, and divide by delta, and let the limit take the limit as delta goes to 0. So this kind of idea seems plausible for small delta. Right. So this is, I guess, the idea behind Buffin's needle, but there's also a theorem associated to it, which is precisely the following. If you do this experiment, then the expected number of intersections between the needle xy and the boundary of f, okay, you shouldn't just look at whether or not it intersects. You should look at the number of intersections, because it could intersect the boundary more than once, is exactly equal to the surface area, or perimeter in 2 dimensions, times the length of the needle, times a dimension-dependent constant, which I'll write beta n. This thing, I could say what it is explicitly, but let me just remark that it's on the order of 1 over root n. It's 1 in 1 dimension. And this is not too hard to prove. You should think about why it's true, or try to prove it. Let's say when f is a polytope, it has flat sides. And you can think about why this is true. Yes, yeah, this is a known fact from integral geometry. It holds if f has like piecewise C1 boundary. Yeah, this is Cauchy-Crofton formula or something. Yeah, so that's a theorem. And it suggests why an algorithm that does something like this might be a good idea. But in fact, if you think about it at first, you think, oh, this is great. I mean, the surface area up to this factor that I know, and the factor that I know is just this. Why don't I just estimate this empirically? Well, the problem is you can't easily count the number of intersections between the needle and the boundary.
That's the one.
Part of the dimension 1 problem, yeah. But you do have something that you can say. You can at least say that in this setup, the indicator that f of x does not equal f of y is less than or equal to the number of intersections. Okay, because if they're not equal, this is 0, nothing matters. If they are not equal, then it has to cross the boundary somewhere. Now, the thing is, this could be not equality, right? I mean, it could cross the boundary 2 times, and then these would be not equal, or 4 times. So it's just an underestimate. But there's an intuition, at least, that somehow if delta is small enough, it should somehow be unlikely to cross more than once. Okay, but the fundamental problem with like turning this into an actual proof in algorithm and analysis is understanding what does it mean small enough. There's actually one other more minor issue, besides sort of understanding sort of how small does delta have to be so that this is approximately correct. There's the problem that even in one dimension, right? Let me draw a tricky example here. Imagine the set looked like this. It was sort of kind of periodic looking. All these intervals have the same width and the same length of gap between them. And imagine delta is this distance. And you see, no matter where I put this delta length needle, either both endpoints will be in or both will be out. So you'll always be counting 0 on the left-hand side, even though the thing has large surface area and large area. Okay? But this sort of issue is a more minor issue. You can sort of easily get around this by, instead of always picking a needle of length exactly delta, randomize a little bit the length of the needle. Okay? And that'll help you solve this problem. Okay? So I hope that's motivation enough for the whole algorithm, which I'll now state. So I'll state the whole algorithm and give a sketch of the analysis, and then we'll be done. In order to state the algorithm, though, I need this notion of noise sensitivity, which Elkanon suggested. And I should also add that this idea of using noise sensitivity was crucial to this statement I erased here, the BBBY paper, Blay et al., or Balkan et al. The idea of using noise sensitivity to do the test and analyze it came from that paper, actually, even though it was only one dimension. So let's define, this is slightly non-standard notation, but I hope you'll be okay with it. I want to define T delta of f. That's another function from, let's say, the torus into the interval minus 1, 1. It's just its value at a point x is the expected value of the indicator f of y, where y is drawn not just a random point at distance delta from x, but a random point in the ball of radius delta centered at x. Okay, so if, let's say this is the picture. Here's the set f. Little f is plus 1 inside and minus 1 outside. The value of t rho or t delta f at this point is, you average the indicator around a little ball here, so it would just be 1. Probably around here it would be around 0, because about half the points are in and half the points are out, etc. And with this in hand, we can also define the noise sensitivity of delta at f to be this. The probability when x is drawn at random from the torus and y is drawn from the ball of radius delta around x, that f of x does not equal f of y. Okay, so this is exactly like this needle experiment, except you're sort of randomizing the length of the needle. Okay, and in fact, let me just make a little comment here that in this definition, the expected length of xy is delta times, does anybody know what the expected length of a point inside the unit ball is? That one has a simple formula. It's n over n plus 1. But this is the expected length of a vector chosen randomly from the interior of a unit ball. Okay, so that's the definition of noise sensitivity, and we can also write it in a way that involves these other things we just defined. That's the same as the expected value over a half minus a half times f of x, f of y, because this whole thing is the indicator that f of x does not equal f of y, which is a half times the expectation over x of 1 minus f of x times t delta f of x. Yeah, these are all the same thing. Yeah.
So this needle thing is very sensitive. This seems to be very sensitive, but this measure seems to be more robust. Is that true?
Well, this event is kind of doing the exact same thing as, or talking about the exact same thing as this, except it's just randomizing the length of the needle a little bit.
So both of them will be...
I guess so. Okay, so now I can state the actual algorithm. And it's just the same idea as this. Okay, so the actual algorithm is you're in step 0, you're given access to F and epsilon and the target surface area S. And given these parameters, you set delta to be something. I'll say later. And then in step 1, you just empirically estimate the noise sensitivity of little f at delta. Okay, using, it turns out that it'll be enough to use order 1 over epsilon many queries. Okay, so you just do this experiment a bunch of times, make 2 queries and estimate. Okay, and by Chernoff, you'll get a very good estimate. So it's basically as if you actually knew the noise sensitivity at delta of f. Well, it actually depends like how big this quantity I'm trying to estimate is. And I actually won't eventually get into the exact details of the query complexity, but it's all standard Chernoff stuff. Maybe actually it'll become clear in a second. Okay, and then finally, step 2, having estimated this, just say yes if and only if the estimate is at most 1.01 times beta n times s times n over n plus 1 times delta. Okay. So, let me first, pardon me? This which? Beta n is, yeah, from this thing. So this is set up so that the completeness of the test will be clear. Well, I mean not clear, but it'll happen automatically from this theorem. So the point is, let's assume that you get like a completely accurate estimate of the noise sensitivity, which you do by Chernoff. Then Buffin's needle tells you that the noise sensitivity, which is the empirical estimate of how often this happens, will be less than or equal to the expectation of how often this happens. And if the true surface area is at most S, then this will be at most, beta n times S times delta times, well, not times delta, but times the expected length of the needle. And as we saw here, the expected length of the needle is n over n plus 1 times delta. Okay. So, any questions about the completeness? So now we come to this is set up, this is always an underestimate, so this will be okay. Now we come to the main question of hopefully somehow if delta is small enough, this is maybe approximately correct or not too much of an underestimate or what have you. Okay. So the soundness. That was crazy. Thank you. The soundness is, okay, so actually I should tell you how you set delta. In fact, how you set delta so that this thing is epsilon. Delta is set such that this quantity is 0.01 epsilon. And that's basically why order of 1 over epsilon queries are needed, because you're estimating something that is, you're basically trying to tell if it's on the order of epsilon or not. And you don't mind a multiplicative factor of 1.001, so that's why O of 1 over epsilon is okay. And the soundness theorem is that if the noise sensitivity of F is at most 0.01 epsilon, then there exists a G which has two properties. First, its surface area is at most this dimension-dependent constant kappa n, which is like 4 over pi plus 0.001 times S. And the volume of F symmetric difference G is at most epsilon. Okay. All right, so in the remaining 7 minutes, I'll try to sketch the proof of this. Okay, so let me make one quick observation. The hypothesis of this theorem is that, epsilon is bigger than or equal to the noise sensitivity at delta of f. Okay, and let me use this formula here. So that's bigger than or equal to a half times the expected value over x of 1 minus the absolute value of t delta f of x. Okay, just using the fact that f is at most 1 in absolute value. Okay, and the assumption is that this quantity is at most, basically epsilon, which means that this quantity, absolute value of t delta f of x, which let me call this g of x, is basically almost always plus or minus 1 on average. Okay, roughly speaking, this hypothesis means that this g of x is sort of always plus or minus 1, maybe minus plus theta of epsilon. Okay, so it's sort of almost always 1 or minus 1. And furthermore, it's sort of this thing more or less always agrees with f of x. It's mostly 1 where f is close to 1 where f is 1 and close to minus 1 where f is minus 1. So you might imagine in this picture, remember here f is plus 1 everywhere inside this set and minus 1 elsewhere. G is maybe going to be like plus 1 sort of well inside this set, and it's going to kind of tail off to around 0 here. It's going to be kind of minus 1 everywhere outside this set. Maybe it'll even be close to minus 1 on this little tentacle. It'll kind of smooth out. Okay. So what do we have to do? Given this fact that G is kind of always close to plus or minus 1, we need to build capital G out of little g in such a way that has small surface area and also it's similar to f. Now, a natural idea is like, okay, we need to build capital G out of little g. So any place where like little g is plus 1, we should put that into capital G. And any place where it's minus 1, we should, declare that to be outside of capital G. If you're close to plus 1, maybe you should also be in capital G. If it's on the gray area, maybe you're not so sure, but it's okay. It's rarely sort of in the gray area. So actually, in some sense, satisfying this condition is not very hard. But satisfying this condition is hard. Like, you have to build a G that has small surface area. So somehow, like, you have to like thread the needle. You want it to be this part to be outside of G, this part to be inside G. You kind of have to figure out how to put in like a small surface area set here. And we spent some time thinking about how to do this, and it was getting really complicated seeming. But then we resorted to maybe the obvious idea, which somebody might be able to suggest. Can you suggest maybe a strategy? Yes, you should look at level sets, super level sets, and you should do it randomly, because, what else are you going to do, right? The probabilistic method. Yeah, so the idea is to define G to be the set of all x where G of x is bigger than some threshold theta, where theta is chosen randomly. And I should say, if there's like one part in this paper where I think we did something a little bit smart and can pat ourselves on the back, it's to have the idea of not choosing it uniformly randomly, but the way that makes it work out quite slickly is to choose it from the triangular distribution, for a reason you'll see. The distribution with PDF, this PDF. Okay, so somehow a little bit more biased towards being around 0 than plus or minus 1. Okay, so this is our strategy. Actually, it would still work if we had chosen it from the uniform distribution. We'd just get worse parameters. I think I can erase this. As I said, the second condition, that the set G you get out is similar to capital F. It's not hard. It's very easy, in fact, basically because of this observation that G more or less agrees with little f. So in fact, showing that the expectation over theta of f symmetric difference G is at most epsilon is easy. me skip that. You can even show that it's at most this with high probability just using Markov or something. But the main thing is to bound the expected value, again over theta, of the surface area of G. Okay, because it's kind of constructed in somewhat a weird way. And we're going to show that it's at most this in expectation, so probabilistic method, if we make this high probability, then the right G will exist. No. Actually, we don't even use... Yeah, I mean, you can pay a little bit here with Markov and then suffer a lot here with Markov. It's actually even, what we really do is like change this so it's like this. And then we get this holding with probability 1. But there's a variety of simple ways you can do it. But what are we going to do about this? The expected surface area of G. So remember, basically think of G like a terrain. This is 2 dimensions. Little g is like this function that's -1, between -1 and 1. And like we pick a random height, and we take all the set where little g is bigger than that height. And then we're interested in the surface area of that. But even though it seems like a complicated construction, there's actually simply like an exact formula for what this is. Does anybody know the name of this theorem? Yeah, who said it? Yeah, we got a real mathematician back here. This is the co-area formula. And it just gives you an expression. It's equal to the expected value. It's kind of basically equal to the expected value of x of the length of the gradient of little g at x. Actually, it'd be exactly this if I had picked theta according to the uniform distribution, maybe up to a factor of 1/2. In general, if you don't pick it according to the uniform distribution, you should put in phi, the PDF of g of x here. This formula looks a little opaque, but I highly recommend you think about this formula, let's say in the uniform distribution case, in which case this PDF is simply constantly 1/2, and that factor goes away, and n equals 1. So imagine you really have, here's n equals 1, little g is some function that looks like this maybe. And the experiment is like you pick a random height, theta, and you look at the surface area of this set where it's bigger than that. So you look at the surface area of this set, which is like 1, 2, 3, 4, 5 boundary points. And in expectation, that's the same as the average length of the derivative of g. So it's fun to see why that's the case. Think about it like a particle traveling here, and you're measuring the total distance it drives with the expected length of the derivative. It's like you can measure how far the car drives by like picking a random point and seeing how many times the car crosses that point. In 2 dimensions, it's a little less easy to see, but it's some kind of like Fubini theorem that lets you measure sort of g's height by like crossing it by cross sections. Anyway, it's a theorem which luckily helps us out and actually makes our work almost done. Yeah, so this gives us an exact expression for this. And we need one little claim, which is not hard. How are we going to bound the length of the gradient of g? Well, I claim that g is O of 1 over delta Lipschitz. And this O actually depends on the dimension n. In fact, it's like it's like root n, but don't worry about that. Think about 2 dimensions if you want. And that's because what is g? It's t delta f. And so if you're thinking about what Lipschitz constant it has, you pick 2 points at distance delta. You average little f in a ball around this one. You average little f in a ball around this one. Well, those averages can't be too different if delta is close, because f is bounded between -1 and 1. In fact, the max it could be is just the total variation distance between the probability distribution, which is uniform on this ball, and the uniform on this ball. And the balls like overlap if delta is small. Okay, so you can just compute it. The overlap depends on the dimension. It's something like root n, but it's 1 over delta is the Lipschitz constant. Yes. Yeah. So with this in hand, we're kind of in good shape. because this G is Lipschitz, so I mean that just immediately shows that this thing is like at most, okay, this order 1 over delta. Let me put in the dependence on n, root n over delta. So we get that this thing is at most, okay, order root n over delta times the expected value of phi, which I erased, but it's the triangle distribution. So this triangle distribution is phi of t equals 1 minus absolute value of t. So we get expected value of 1 minus absolute value of g. Okay, and that's exactly this. So this is at most 2 root n over delta times the noise sensitivity at delta of f. Okay, and the thing that our tester tested, if you remember the algorithm, we're basically done now, but the thing that our tester actually tested is whether or not the noise sensitivity at delta of f is at most beta n times n over n plus 1 times the target s times delta. So if the tester passes, the noise sensitivity is bounded by this. So the deltas cancel. The n over n plus 1 is basically a constant. And I told you this is like theta of 1 over root n. So the root n's kind of cancel, and eventually you get that this is some dimension-dependent constant, but it's actually constant for all n times s. Okay, and if you work through the things very carefully, this is exactly the kappa n, which is got this funny formula that's 1, luckily in dimension 1, and it increases to 4 over pi as n goes to infinity. Okay, so that's it. I think a good open question is try and get rid of this kappa n, and it could be that the algorithm already does it. We just need to improve the analysis. Okay, thanks. Yep.
You choose that this is not to be delta, but you choose kind of a random point in the delta ball, right?
Yes.
So,
yes.
So if you play around with this, how does that kind of change?
Yeah, that's a very natural idea. You should play around with this. It affects things in two ways. This n over n plus 1 is coming from the average length of a point drawn from that distribution. And it also enters here in the total variation distance between the distribution centered here and the distribution centered delta away. And by trying different distributions, you can make things, well, potentially better or worse. The best we were able to make them was by taking it to be uniform over a ball.
So it's better than Gaussian?
It was about the same as Gaussian, I think, if n is high dimensions. If for constant dimensions, for example, in one dimension, if you do it with the ball and you're very careful, you get 1 out here, which is great. You can't beat it. And I think the only way you can get 1, this is exactly what happened in Eric's paper, is by using uniform distribution over a ball, which is just an interval in one dimension. And it's worse if you would use a Gaussian. For the analogous result for testing Gaussian surface area, we naturally use the Gaussian noise sensitivity with the Ornstein-Uhlenbeck thing. And when you do all the calculations, you get 4 over pi out, and that's the best distribution we could think of there.
Epsilon close to a body with surface area so much.
Yeah, if you have a body in Gaussian space, and it's like noise sensitivity is like, there it's like root delta instead of delta, but we know that the Gaussian noise sensitivity is always less than or equal to surface area times root delta times some funny constant. And this kind of tells you that the inequality also goes the other way. If you're willing to be epsilon close to having small surface area, you lose another factor of 4 over pi, and the epsilon is whatever noise sensitivity at delta itself is, basically, I think. So yeah, it kind of allows you to reverse this inequality relating Gaussian noise sensitivity and Gaussian surface area.
I have a quick question. Did you guys think at all about extending this to the Boolean cube with like the notion of surface area for subsets of the cube that Alkanon mentioned?
Oh, nope, we did not. Yeah. It's a similar flavor of problem, yeah, so maybe you could try that.